Okay, logarithmic functions. It's the inverse of an exponential function. If you have log base b of x equals y, that's the same thing as b to the y equals x. Because remember, a logarithm is just an exponent. Okay, a log is equal to an exponent, and the base stays the base. So if I wanted to take this and convert it, it's that the b stays the b. You come over here, you pick up the exponent, and then that equals x. All right. The inverse now, the inverse of an exponential function is a little bit different. That's like y equals a to the x. That is going to be, instead of that, it's going to be y equals log base a of x. Those are inverses, okay, where you don't switch the x and the y kind of thing. All right, so now solve for x by rewriting. All right, so what I want to do is I want to take these logs and rewrite them in exponential form. So it's 3 squared equals x. That gives me a 9. 9 equals x. Okay, next one here. X squared equals 9. I'm going to take the square root of both sides here. So I get x equals, and when you take the square root of 9, it's going to be plus or minus 3. Here's the issue, though, okay? I cannot have a negative base, so I'm only going to keep the positive answer there, so it's x equals 3. Now, for this one here, it is 2 to the x equals 8. I've written that in exponential form, because remember, the log is equal to the exponent, so the exponent is x in exponential form. So 2 to the x equals 8, and when I have 2 to the x equals 8, I can use like bases here to solve this, right? This is 2 cubed, this is 2 to the x. Okay, and then once I have like bases, I can drop the bases and have x equals 3. Let's say you didn't recognize the like bases there, right? What we can do here is we can take the log of both sides of this, and wait a second before I get too far, because I think I'm going to do that down here. Right? Sure. Yeah. I'm going to do that down there. So I'm just going to kind of hold off on that for right now. All right, properties of logarithms. All right, if I have the log of a product, so like the log of a b, that is equal to log a plus log b. It's equal to the sum of the logs. All right, and then the log of a quotient, the log of a over b, is equal to the log of a minus the log of b. So I can take and expand an expression that is the log of a quotient into the difference of logs, or I can condense it into a single log, taking the subtraction and turning it into a quotient. And then the power rule, okay? And this is kind of the most powerful one here. And by the way, these bases could be anything. I could have log base 2, right, of x to the third, all right? Well, what that is, it's just going to be 3 times log base 2 of x, all right? And I could also have ln, right? Don't forget about our friend ln, right? So if I have ln x squared, that is equal to 2 times the ln of x, something like that. Change of base, I don't teach change of base anymore, right? I teach you guys to write in exponential form and then take log of both sides, and that is effectively the same thing as change of base. The last thing we need is another thing to memorize. All right, so if I have expand log x squared y over z, that's really kind of, this is the way it should be written probably. There you go, so you can see it properly as a quotient. All right, so if it's a quotient, it's going to be the log of x squared y minus the log of z. I'm expanding this. I'm kind of like stretching it out. All right, so now I have the log of a product. So that's going to be log x squared plus log y, and then that's minus log z. Now, since the order of operations are okay here, I don't really need parentheses around these first 2 logs. And then the last thing I do is 2 log x plus log y minus log z. Okay, and that last step I apply the power rule. The first step I use the quotient rule to make it subtraction, and then that was the first step, and the second step I use the product rule to make it addition, and then the third and final step I use the power rule to change this first term to 2 log x. Okay, now condensing is going the other way, all right? And just like order of operations, you got to kind of condense inside the parentheses first. Okay, so I'm going to just bring down this 3 log x minus, all right, and then this right here, a log plus a log, is the same thing as the log of a product. And this is 2 to the third, I apologize, 3 to the second, right? All right, so that's going to be log y times 3 to the second, which is what, 9? I think that's 9y. Let's simplify that. Okay, so I'm going to do log 9y. There we go. And this one here, log 3 log x, is log x cubed. My whole goal here is to get this written as a single log. All right, and then the last thing I can do here is log x cubed over 9y. And there it is, written as a single log. So when it says condense or write as a single logarithm, you're going to go that way. The first rule I applied was the product rule, where I took the sum of the logs and turned it into a product. And I used the power rule here, right? Because I needed to so that I had a log plus a log. Before I can add those logs, it has to be, I can't add log and 2 log. I have to turn it into log 3 squared first. All right? Equations using logarithms. All right, so the advice here is to condense. If you have log on both sides, you're going to drop the log. Otherwise, you're going to rewrite it as an exponential. And if you cannot solve the exponential, take the log on both sides and use the power property. All right, and that's kind of instead of the change of base thing that we're talking about. All right, so here we go. I have 5 to the 3x plus 1 equals 7. So the first thing I want to do, just like all other problems in this class, is get the weirdest looking thing alone. So the weirdest looking thing in this problem is 5 to the 3x. So I'm going to subtract 1 from both sides. That's pretty basic, right? 5 to the 3x equals 6. All right, and now, these are obviously not like bases, and I could let y1 equal 1 or y2 equal the other, but let's say it said only an algebraic solution will be accepted. So what I'm going to do is I'm going to take the log of both sides. Now what I can do is I can use the power rule to bring this 3x down off the shelf, or I can do something with it. I rewrote that as that, and now you can see I can divide both sides by log 5, and I'll get 3x equals, and this can be done on the calculator, right? Log 6 over log 5. There is no base button on here, right? The only thing I can do is either a log base 10 or a log base e with these, all right? So I have log of 6 divided by log of 5, okay? Make sure you close that parenthesis after the 6, because I don't want to do 6 divided by the log of 5 and then take the log of that, all right? And there we go. I got 1.11328753, right? And I'm going to divide that by 3, okay? So this 3x equals 1.1132827753. And just write it all, okay? Just write it all. Now divide both sides by 3, and write on the calculator, divide by 3. Don't round until you get to the end, okay? You don't want to make rounding errors because you just started rounding too early. So whatever, I'm going to say solve this to the nearest 10th, right? So it's x equals 0.37. That's what I got, okay? There we go. Next, log 5x plus log x minus 1 equals 2. So see what I have here is I have 2 logs, but I have a log plus a log. So I can condense this into log of 5x times x minus 1. And notice these are both base 10, right? Because there's nothing written there. When there's nothing written there, log base 10 equals just plain old log, right? And log base e is the same thing as ln, right? Just a side note there. All right, so now I have this written this way. This is base 10, so I'm going to turn this into exponential form. Keep the base of 10, raise it to the exponent, because the log is equal to the exponent, and then I'm going to distribute this guy at the same time. Okay, so I get 5x squared minus 5x. All right, and then 10 squared is 100. So I get 0 equals 5x squared minus 5x minus 100. All right, just like that. And, you know, if it's factorable, you can go ahead and factor it. You know, I'm not sure if it's factorable. Let's see, 5 times 20, 25, yeah, sure. All right, so if I have a 5, I can factor out a 5, first of all. Factor out a 5 from every term. So my GCF is 5, I get x squared minus x minus 20. And then it's an easier thing to do. Does 5 ever equal 0? No. Okay, so I set that first factor equal to 0, and it didn't really get me anywhere. But now I set this one equal to 0, and I have x minus 5 times x plus 4. That's going to equal 0. I get x equals 5, and I get x equals negative 4. All right, the last thing I need to do is I need to make sure I'm not taking the log of a negative number. All right, if you can see here, if I put 5 in for x, I am doing the log of 25. That's okay. All right, and the log of 4, and that's fine too. The issue arises if I try and use this -4 here. 5 times -4 is like -20. I can't take the log of -20. That -4 is an extraneous solution. My answer is just 5. Okay. And let's see. I think this is our final example here. So we got a bunch of log base 6s. Okay, these are log base 6. All right, and look, it's log base 6 of something minus log base 6 of something equals log base 6 of something else. So what I can do is I can turn this into a quotient, 3x plus 4 over 5, and then that equals log base 6 of 2x. Now in this case, I have the log equal to log. I can drop the logs off. The only way this is possible is if the only way this can be equal here, like we've stated, is if 3x plus 4 over 5 is in fact equal to 2x. I can put that guy over 1, and now I can just cross multiply. So I'm going to get 3x plus 4 equals 10x. I'm going to subtract 3x from both sides, so I get 7x equals 4. And then my final answer is x equals 4 over 7. So I've solved for x. I put a box around it. I was a little maybe hasty. I need to make sure that I'm not taking the log of a negative number. This is a positive times a positive plus a positive, so that's positive. That's 5. That doesn't even affect anything. And that one would be 8/7, which is obviously positive as well. So that is, in fact, my answer. Okay? Yeah, so that's kind of it. Maybe I should just show you one real quick where the log doesn't drop off. So we're going to add bonus example here, all right? Bonus example. I'm going to take and do log base, 6 of x plus 3 equals, log base 6 of, let's do 5, and then that equals like, say, x, something like that, all right? So what I have here is I have something that I can't punch into my calculator because I can't do base 6 on my calculator. All right, what I can do is rewrite this as an exponential. 6 to the x equals 5. And now I can let y1 equal 6 to the x, and I can let y2 equal 5, and I can graph both of those. I can't graph log base 6 of 5. This is not, I can't put it into my calculator. All right, so I could do this and get a y1 and a y2 and solve graphically, or I could take the log of both sides. Now this is the log, or I could do the ln, by the way. All right, either one. All right, what I typically use is the log with the base 10. All right, so now I have taken the log of both sides. If these two are equal, then the logs of those things should be equal as well. All right, so now that I have taken the log of both sides, I'm going to use the power rule to rewrite that one, okay? And this is where it's like the change of base. This is like kind of what the change of base is equal to here. It's going to be x equals log base 5 over log base 6. And then that can be evaluated on the calculator, okay? Log 5, close that parenthesis, divided by log 6. And then I get an answer. All right, x equals 0.898. So what 0.898, right? I don't, didn't say where to round it to. So that's an acceptable solution. Okay, I think that's kind of comfortably it for, again, a brief review of logarithms. We will be doing some log and exponent review questions in class tomorrow, and you're going to continue to see them in your Regents reviews. Okay, thanks. Good luck.